Mambo, and welcome to the last part of our Unit 6 presentation on database design and denormalization for CIS 3107 database modeling. We will be covering sections 6.7 through 6.9 in our text. In this presentation, we will learn that normalization and ER modeling are used concurrently to produce a good database design, and some situations require denormalization to generate information efficiently. Normalization procedures can be used to produce good tables from poor ones and should be part of the design process. Therefore, make sure that proposed entities meet the required normal form before the table structures are created. You might be asked to redesign and modify existing databases that are in effect anomaly traps. Therefore, you should be aware of good design principles and procedures as well as normalization procedures. First, an ERD is created through an iterative process that has you identifying relevant entities, their attributes, and their relationships. Then you use the results to identify additional entities and attributes. The ERD provides the big picture or macro view of an organization's data requirements and operations. Second, normalization focuses on the characteristics of specific entities. That is, normalization represents a micro view of the entities within the ERD. To understand the proper role of normalization in the design process, we will re-examine the operations of the contracting company summarized by the following business rules. The company manages many projects. Each project requires the services of many employees. An employee may be assigned to several different projects. Some employees are not assigned to a project and perform duties not specifically related to a project. Some employees are part of a labor pool to be shared by all project teams. For example, the company's executive secretary would not be assigned to any one particular project. Each employee has a single primary job classification, which determines the hourly billing rate. Many employees can have the same job classification. For example, the company employs more than one electrical engineer. Given that simple description of the company's operations, two entities, project and employee, and their attributes are initially defined. Project has project num, project name, and employee has employee num and employee last name and employee first name, employee initial, job description, job change per hour. Those two entities constitute the initial ERD shown in figure 6.13. After creating the initial ERD shown in figure 6.13, the normal forms are defined. Project is in 3NF and needs no modification at this point. Employee requires additional scrutiny. The job _ description attribute defines job classifications such as system analyst, database designer, and programmer. In turn, those classifications determine the billing rate, job _ change _ hour. Therefore, employee contains a transitive dependency. The removal of employee's transitive dependency yields three entities: project having project _ num, project _ name. Employee with employee _ num, employee _ last name, employee _ first name, employee initial, and job code _ code. Job with job _ code, job _ description, and job _ change _ hour. Because the normalization process yields an additional entity, job, the initial ERD is modified as shown in figure 6.14. To represent the many-to-many relationship between employee and project, you might think that the two one-to-many relationships could be used. An employee can be assigned to many projects, and each project can have many employees assigned to it. See figure 6.15. Unfortunately, that representation yields a design that cannot be correctly implemented. Because the many-to-many relationship between employee and project cannot be implemented, the ERD in figure 6.15 must be modified to include the assignment entity to track the assignment of employees to projects, thus yielding the ERD shown in figure 6.16. The assignment entity in figure 6.16 uses the primary keys from the entities project and employee to serve as its foreign keys. However, note that in this implementation, the assignment entity's surrogate primary key is assign _ num to avoid the use of a composite primary key. Therefore, the quote, enters, end quote, relationship between employee and assignment, and the requires, end quote, relationship between project and assignment are shown as weak or non-identifying. Although the creation of normalized relations is an important database design goal, it is only one of many such goals. Good database design also considers reporting requirements and processing speed. The problem with normalization is that as tables are decomposed to conform to normalization requirements, the number of database tables expands. Therefore, in order to generate information, data must be put together from various tables. Joining a large number of tables takes additional input-output operations and processing logic, thereby reducing system speed. The defects in unnormalized tables are found in data updates that are less efficient because tables are larger. Indexing often becomes more cumbersome, as well as the strategies for creating virtual tables, known as views. The problem with denormalized relations and redundant data is that data integrity could become compromised due to the possibility of insert, update, and deletion anomalies. The advice is simple. Use common sense during the normalization process. Furthermore, the database design process could, in some cases, introduce some small degree of redundant data in the model, as seen in the implemented database here in Figure 6.17. This, in effect, creates denormalized relations. Table 6.6 shows some common examples of data redundancy that are generally found in database implementations. An example of storing zip and city attributes in the agent table. When zip determines city, avoids extra join operations as a program can validate city using a drop-down box based on the zip code. Another example of derived data is storing student underscore hours and student underscore class, student classification, when student underscore hours determines student underscore class, thus avoiding the extra join operations by having a program validate the classification based on the student hours. In summary, the larger the number of tables, the more additional input-output operations and processing logic you need to join them. Therefore, tables are sometimes denormalized to yield less input-output in order to increase processing speed. Unfortunately, with larger tables, you pay for the increased processing speed by making the data updates less efficient, by making indexing more cumbersome, and by introducing data redundancies that are likely to yield data anomalies. In the design of production of databases, use denormalization sparingly and cautiously. Thank you for viewing our Unit 6 Part 3 presentation. The diagrams and content of this lecture were derived from our textbook. For more detailed treatment of these concepts, please review pages 226 to 233 in our text.